Every star, planet, tree, and ocean you have ever seen or interacted with belongs to a very narrow slice of reality. If you put everything humanity has ever mapped onto a scale, you would find a massive gap in the math. This pie chart shows the total composition of the universe. All the visible material accounts for roughly 5%. The remaining 95% is split between two massive, entirely invisible components: dark matter at 27% and dark energy at 68%. We cannot see, touch, or directly measure either of them. These two components perform different roles. One provides the gravitational weight that pulls matter together, while the other generates a pressure that pushes space apart. To understand the laws of physics and the ultimate fate of the universe, we have to determine which of these invisible forces is winning. Under the standard rules of gravity, proximity equals speed. In our own solar system, Mercury orbits the Sun incredibly fast because it is close to the Sun's massive gravitational center, while Neptune sits far away and moves at a crawl. This graph compares standard expected orbital speeds against actual observations. In the 1970s, astronomer Vera Rubin measured distant galaxies and found that stars at the extreme outer edges spin at the exact same high speeds as the stars tightly packed near extreme center. If those outer stars are moving that fast, the visible mass of the galaxy does not generate enough gravity to hold on to them. The galaxy should rip apart. But since they stay intact, physicists deduce that an invisible halo of extra mass envelops them. This unseen material provides the gravitational glue holding the spinning stars together. Scientists call this dark matter. The leading theory is that it is made of weakly interacting massive particles, or WIMPs. These particles have mass, but they pass through normal matter without hitting it or reacting to light. Proving they exist requires burying massive, highly sensitive detectors deep underground to shield them from cosmic radiation. Scientists are waiting for a single WIMP to accidentally collide with an atom of regular matter. Dark matter is the local attractive force. It makes the existence of stable galaxies and our own lives possible. Because gravity pulls things together, physicists assumed for decades that the initial expansion of the Big Bang must be slowing down over time. In 1998, two independent teams of astronomers measured exactly how much that expansion was decelerating by tracking the distance and speed of exploding stars. They found a paradox. The expansion of the universe is accelerating. Imagine tossing an apple straight up, and instead of falling back to your hand, it shoots into the sky faster and faster. This smooth, repulsive force pushes space apart on a universal scale. Scientists call it dark energy. The leading explanation for this force brings us back to Albert Einstein and a concept he called the cosmological constant. In quantum physics, the vacuum of space possesses its own inherent repulsive energy. As the universe expands, new empty space is created, which generates even more energy to drive the expansion faster. Dark energy is a repulsive property of the void itself. It dictates the growth and expansion of the entire cosmos. Billions of years ago, the universe was smaller and denser. Because everything was tightly packed, the gravitational pull of dark matter was highly concentrated and dominant. This allowed vast clouds of cosmic dust to be rapidly pulled together, forming the very first generations of stars and galaxies. As space expanded, dark matter became diluted and its gravitational grip grew weaker, but dark energy remained at a constant density.
Roughly 5 billion years ago, they crossed paths. Dark energy officially overtook dark matter. We now live in a universe firmly controlled by dark energy, accelerating apart faster every second. Until we capture a WIMP or decode the energy of a vacuum, humanity remains a group of 5% observers in a universe whose laws are mysterious, broken, and tearing themselves apart.